Hi, this is Christoph speaking, and welcome to the online lecture for the Digital Methods course for Ghent University and of course also for the BScSS students on natural language processing, or in short NLP. I can imagine that the concept doesn't mean anything to you, that it's completely new, that you have no clue what it is all about. This is fine because this is also the starting point I'm taking here. I hope and that at the end of the lecture here that you have a basic understanding of the fundamental concepts, of the basic techniques, and some of the typical issues surrounding NLP. Now, where does this lecture fit within the digital methods course? Maybe that's a good question to ask since we had to move everything online all of a sudden due to the corona crisis. Well, it's a good idea to view this lecture somewhere near the end of March, beginning of April, between the data collection phase and the data wrangling phase. And it's also meant for everyone. So all students of the digital methods course should watch this and also study the material, right? It's just part of the material you have to study for your theoretical exam. So what will we cover today? First, I'm going to give you a straightforward definition of NLP, what it's all about, and I'm going to discuss some related terms such as machine learning and AI. I'm also going to talk about the role of knowledge engineering versus machine learning, which is something that I use as a framework throughout the entire lecture. Then I'm going to give you some examples. In your everyday life, also in the private sector, there are a lot of applications of NLP, and we're going to discuss a couple of them. And especially relevant to us academics, I'm also going to discuss how scientists or communication scientists in particular are using NLP in their research. And then the third block, it's also the largest block of the lecture, we're going to actually look at how NLP works. We're going to look at lexicons and rule-based lexicons, how they work, why they're not sufficient to do some proper NLP analysis. And then we're also going to talk about machine learning in NLP, which is basically constructing predictive models for language processing. And lastly, I'm going to talk about a couple of issues in NLP, a couple of points where the field is struggling, or some typical examples of bottlenecks when it comes to NLP analysis. So first up, what is natural language processing? When we talk about natural language processing, we are referring to a set of methods for making human language accessible to computers. Imagine that you're feeding a piece of text to a computer. In and of by itself, the text doesn't mean anything to the computer. To the computer is just a series of ones and zeros, of bits and bytes. NLP refers to all those techniques that allow the computer to extract something meaningful from said piece of text. In the most basic sense, a simple spell check on your computer is an NLP application. We feed a computer with a dictionary, and the computer could guess which word you were trying to type and what kind of errors that you make. But also, the spam filter in your email is a typical NLP application. The algorithm scans the title and the content of your email, and based on a very simple algorithm that we will talk about later, it decides whether the email is spam or not. In other words, you're feeding the computer a piece of text and it extracts something meaningful out of it. In this case, a label, the email is spam or it is not spam. In other words, NLP is all about analyzing, understanding, and even generating text in a meaningful manner by computers. NLP is considered a subset of artificial intelligence. AI is all about simulating human intelligence, or this is in any way the end goal. We're not there yet, not even close. Now, language is obviously the marker of human intelligence. We're not only communicating in language, we're even thinking in language. So in some sense, being human is understanding language. It's what makes us human. So if you ever want to build software that simulates or mimics human intelligence, and even in the end robots, well, we need NLP. Much of NLP relies also on machine learning. Machine learning are basically models that make predictions or decisions made by algorithms in an automatic fashion, so without human intervention, or anyway without much human intervention. Machine learning is used all over the place. For example, a stock market is basically run by machine learning algorithms. These algorithms decide whether to buy or sell stock, and they do that just in a split second without much human intervention. This is the reason why some economists say that we don't understand how the modern economy in the 21st century actually works, because it's all done automatically. The decision process is basically outsourced to algorithms. And these applications have exploded recently in the digital age, especially in the 21st century. Well, why is that? Well, to make computers understand language, we need to feed it a lot of examples. This is something we'll talk about later. And in a digital age, we have large text corpora available. For example, you could download the entire Wikipedia archive and use it to feed an algorithm so that the algorithm has a basic understanding of language. Now imagine that you're talking to your voice assistant on your iPhone, Siri, and you tell Siri, can you play me the first album of Jay-Z? First, what will happen is that your voice gets translated to text by speech recognition software. And this is something where NLP can help out as well. But second, and even if your voice is being translated successfully to a piece of text, how can Siri actually understand your sentence and open up Spotify and play the first album of Jay-Z? In other words, how can we make a piece of text meaningful to a computer? Well, there are two different, though complementary approaches to this, and they come from two different intellectual traditions as well. None of these approaches are ideal and are combined in NLP applications nowadays. The first approach comes from the linguistics department, and we know it as knowledge engineering. The basic idea of knowledge engineering is that humans should provide a framework to computers on how language works, and provides the computer a taxonomy of our language, which means all the inflected verbs, for example, so that the computer knows that in the sentences he's working, he works, we want to work, that the word or the verb work refers to the same kind of action. And B, also to give the computer a set of rules how to deal with language so that it mimics human reasoning, how humans think about language and in language. And this is called knowledge engineering, and it was pretty dominant in the 50s and 60s. The people from the computer science departments say now we don't need to feed a computer all kinds of human engineered information. No, computers should just look for patterns within natural language itself and infer an understanding of language from the ground up, from scratch. And this is the machine learning approach. The machine learning approach sees computers as capable of learning, of building information or building an understanding of language from the ground up. Knowledge engineering, not so much. Knowledge engineering sees computers as, let's say, rather dumb when compared with machine learning, and says, no, we humans should design purposefully NLP applications and set the rules on how the computer should analyze and think about language, while the machine learning people say, nah, computers can do that all by themselves. And these are the two approaches, different approaches that are combined in most NLP applications, especially complicated NLP applications today. Basically, what it comes down to is a debate between knowledge versus learning. On the one hand, it's totally unreasonable to follow the computer science fellas and assume that computers will just learn from the ground up what language is and how it works and how you should generate it by feeding it billions of example texts and looking for correlations and co-occurrences within those examples. We still need knowledge engineering and linguistics. We still need to feed or NLP software, semantic relationships, word forms, etc. This is a good example here. So look at these two sentences. Frederik interviewed Rolf. He works for the college newspaper. I'm pretty sure that when I read these sentences aloud that you just knew that the he I underlined here is referring to Frederik and not to Rolf. Now, why is that? That's a good question. Well, it's probably because Frederik is the one interviewing Rolf. And who does interviews? Well, journalists do, right? So, and journalists work for newspapers. And so because we have these implicit relationships of these words in our head, of these concepts in our head, we know or we infer that the he in the second sentence refers to Frederik and not to Rolf. And this is something which is pretty difficult for a computer to just understand and to learn from the ground up just by looking at examples. But on the other hand, we humans are also unable to feed an algorithm all the rules necessary to understand language. So the knowledge engineering has some limitations as well. And this is somewhat of a philosophical argument in the sense that, well, how we humans understand language remains somewhat a mystery to us as well. So we have an innate, a born ability to understand language, but it's pretty difficult or even impossible to make up a set of rules. And if you follow these rules, you will understand every utterance or every piece of text in the universe. Well, this is pretty much impossible. Language is not as straightforward and simple as that. So that means that we also need machine learning. We need machines to implicitly learn how language works by looking at example texts, right? Because we just can't feed it enough rules so that it will understand everything. And this is why both kind of NLP approaches are prevalent in NLP applications today. Knowledge engineering gives the piece of software and a basic framework and understanding of our language, while machine learning gives the application a more implicit understanding of how language actually works without we as humans determining what kind of rules it must follow to extract something meaningful from said text. Now let's take a look at some examples of NLP applications in the private sector and in academia. But first, some examples from the private sector. So whenever you're dealing with language and computers in your daily life, it's probably an NLP application. So the most bare bones example I can give is a spell check. You just feed a computer a dictionary of words, and the computer checks whether the words you're typing in correspond to the list of available words in a particular language. If not, it can guess which word you are trying to type based on how similar or dissimilar the word you typed in is with the words available in a dictionary. Spam filters is also an example I already talked about. Spam filters basically is a classifier or a classification or labeling exercise, which is a pretty popular NLP application. Spam filters want to label certain emails as spam versus not spam, and this is just one example of how NLP can also help us to label or predict textual properties. Social media monitoring, so take a company that wants to know whether the conversations about their product online, on social media, on Twitter, on Facebook, are either positive versus negative in tone, which is what we call sentiment analysis, which is the analysis of emotions in text, which is something we'll talk about later in our NLP workshop. Autocompletion on Google, where Google guesses the word you're trying to type based on the words you already typed, and obviously also based on the searches of other Google users. Summary writing, where you feed the computer a piece of text and it produces a summary to us humans, let's say, and here the challenge is to make said summary comprehensible and meaningful to human readers. Google Translate is another obvious example. It's also incorporated in voice recognition software, again by guessing the words you're trying to say whenever the words are not spoken very clearly. For example, when I say, okay, Siri, can you play me Jay-Z? Well, Jay-Z is not very, clearly spoken, but because I use the word play, it could guess that I'm referring to either a movie or music and thus artists, and so it can make an educated guess that I was talking about Jay-Z. It's also incorporated in other virtual assistants such as Alexa of Amazon and Google Home, and also in chatbots. Now, chatbots is a very complicated application of NLP, and most chatbots are not that clever. For example, Cleverbot Online, and I asked it a question. I said, well, what do you think about this digital methods lecture? And it just said no, so it doesn't think very much, apparently. And the new frontier, let's say, is automatic text writing, where computers generate text from scratch, which is meaningful to us humans. And the ultimate goal here is, for example, to write news articles without any human intervention. This is a pretty neat example of a text summary bot on Reddit, which is a very large online forum. The bot scans all posts and it infers whether the post refers to a news article or not. If it does refer to a news article, it scans the news article and produces a summarized version of said article. I have an example here of an article about, surprise, surprise, the coronavirus. And the bot reduced the article by 66%, which is pretty impressive. The real challenge here, similar to when we humans make a summary of a large piece of text, is to identify the information or the sentences which are key to our understanding of the text and which sentences it could do without and just delete from the entire summary. The real challenges nowadays lie with automated text generation, where the end goal is that a computer just writes pieces of text by itself without any human intervention, so that it could write, for example, news articles or even complete novels. And there were some breakthroughs in this regard. Last year, some researchers released their model called GPT-2. And this model was trained with a, they say simple, but it's not really simple. Let's call it a straightforward objective. Namely, predict the next word given all of the previous words within some text. For example, I gave it a little prompt here. The prompt reads, "This lecture of digital methods is pretty interesting because it's about." And based on this little prompt, the model can guess with a certain, certainty what the next word will be. And it does that based on 8 million web pages. So it looks at the order of the words in these 8 million web pages and the co-occurrences between words in a sentence, etc., etc. And based on the relationships of these words in these 8 million web pages, it can guess what the next word is. It not only does that, it not only guesses the next word, but also the word after that, and after that, based on the previous words. So let's see what the model made of my little prompt here. So I said this lecture of digital methods is pretty interesting because it's about, and on the model, whatever it says after that is based on a model and is not given by me. So because it's about what to do in digital marketing, not just in online marketing. And one of the things that it does is it breaks the whole system down, because instead of thinking about we're just going to socialize more or we're just going to do better PPC, digital methods looks at the whole system and says, okay, let's look at where our fans are located. So it's pretty impressive in the sense that, okay, it's kind of gibberish. It's a little bit marketing talk. So in this sense, it mimics how that real or some humans use language and write language. And it's still pretty, the sentences in and of itself are meaningful. And because it looks so realistic, the model has claimed that the GPT-2 model is too dangerous to be released in full, because you could use it obviously for malicious purposes, such as fake news generation, right? That you could write 100 articles about Donald Trump or Joe Biden, which are completely fake. You could also use it, for example, to generate some tweets and send them out automatically and influence the online conversation purely with this automated text writing model. And for this reason, they didn't release it in full. Of course, it's difficult to distinguish between the real capabilities of these models and the media hype, because the media is pretty quick in hyping all breakthroughs in NLP. But still, as you can see from this example, it's relatively impressive what they can do nowadays. We also use NLP or elements in NLP in academia. When it comes to communication sciences, we usually use NLP to predict or label certain textual properties. So, for example, you want to distinguish between news articles that are fake news versus not fake news, or news articles that are positive versus negative. So that is a typical classifier problem or labeling exercise, similar to what a spam filter does. And usually, or ideally, in communication sciences, the NLP is not the end goal. So the end goal of our research is never to just label texts. No, it's to use these labels and to do something with them. So for example, imagine that we can successfully predict whether a news article is fake news or not. Well, then we can construct a model and see whether certain socio-demographic groups are more likely to click or read on news articles. And then you generate new knowledge and you can add to theory. So NLP should be not an end goal in and of itself, but it's a step or a pre-processing step before actually constructing your model and doing your analysis. The reason why some communication scientists are using NLP in their research is so that they are able to label or predict textual properties in large amounts of text. So I have an example here of a couple of researchers who wanted to know how the media changed their perspective on a specific conflict or issue. And this meant that they had to analyze news articles from the 1990s until 2015, with a total of more than 2,200 news articles. So imagine that you have to read these news articles and to identify some textual properties in his news articles. For example, is this news article dramatized or not? Does it contain personalization? Is it a negative or a positive news article? Etc., etc. If you have to do that manually, it involves a huge cost in human resources. If you could train a model, an NLP model, that automatically classifies a news article as dramatized or not, and it performs well, well, you can just apply it to an endless amount of news articles without any human cost whatsoever. And this is exactly what they did. Now, of course, as you might guess, you could ask some questions on how valid these labels actually are. And we made some comments on that in an upcoming article Frederik and I wrote, and that will be published in the journal Journalism Studies. And it's called What Can Journalism Studies Learn from Supervised Machine Learning? It's on Ufora. Read that article because we made some comments, some critical remarks on using such classifiers to label pieces of text. Researchers can also use NLP to study how humans communicate, or more specifically, how humans communicate online. So this is a pretty interesting example. The researchers here, they collected a huge amount of tweets and they checked those tweets for moral emotional words. Those are words with a heavy emotional valence and that refer to our moral intuitions. In other words, what we think is wrong versus right. I have an example here. So let's take the tweet, "Trump is just evil, shame on him, I'm so angry right now." The tweet contains at least three immoral emotional words: evil, shame, which refer to what we think is wrong versus right, and angry, which has a strong emotional valence. The researchers basically applied a very simple NLP algorithm here, and they just counted certain words. They have basically a dictionary of words, of moral emotional words, and they counted them. Now, if you have to do that manually, it's next to impossible. So that's why they need a NLP, very simple NLP algorithm to do that. And the researchers checked whether these tweets with a lot of moral emotional content are more likely to drive the online social media conversation. And it seems that, yeah, they do. So across topics, you have 3 topics here: gun control, same-sex marriage, and climate change. You can see from these graphs that as a number of moral emotional words in a tweet increases, that their predicted retweet count increases as well. In other words, tweets just like the one on Trump here is more likely to be shared among the Twitter community and to drive the conversation than a tweet which is less angry or less condemning of Trump. And this is an argument, or this is some evidence for an argument to say that social media is partially driven by an outrage machine, because those kind of tweets, they condemn certain people, they condemn certain groups, they make us angry or sad, and these are exactly the tweets that are more likely to be picked up by the Twitter conversation. Now let's take a look how NLP actually works. We start with the most simple or most straightforward approach of NLP, which are lexicons and rule-based lexicons. When we talk about lexicons, we basically refer to dictionaries as defined by humans. So we provide a computer with a basic understanding of a language by providing a taxonomy of our language. So we define which kind of words are verbs, which kind of words are nouns, etc., etc. This is the knowledge engineering part of NLP. This is the part where we humans and how our understanding of our language can inform computers how to analyze texts. And you can use these lexicons in 2 ways. So the first way is to simply identify nouns, adjectives, adverbs, etc., etc. In other words, to define the function of the words in a particular sentence. And this is often used as a pre-processing step. So even if you use a very complex machine learning algorithm, right at the beginning of your analysis or in the pre-processing phase, you want to identify what the function of all the words are in the sentence. And this is something you can only do by just providing it with human-generated knowledge. The second application for lexicons is simply to count a list of predefined words in a piece of text. And this can be whatever you want to look for. So for example, the researchers that counted the presence of moral emotional words in tweets, which I just discussed earlier, is a typical example of a lexicon application. Another typical example is sentiment analysis. Sentiment analysis refers again to the analysis of emotion in text, and this can be categorical or interval based. In other words, a sentiment dictionary or lexicon is basically just a list of words with certain labels. And these labels can just be categorical in the sense of this word is positive or negative. Let's say terrible. Terrible can be labeled as negative, or it can be interval based. Terrible can have a score, a valence score, for example, between -1 for very negative and 1 for very positive. When we take the example of the word terrible, it will have obviously a negative valence score of, let's say, -0.7. And what lexicon approach to sentiment analysis will do is simply count words in the text and count the scores and take an average, and then you have your average sentiment score. That's all. Let's take a look at a specific example. So imagine that I have a lexicon of a couple of thousands of words, and I gave them all a sentiment score from -1 to 1. I have the first sentence here. Let's say it's a review for a restaurant, and the sentence reads, "This restaurant had some delicious food. I recommend it." Okay, the computer scans the text and matches it with our lexicon, and it matches 2 words, delicious and recommend, which both have a positive score of 0.8 and 0.7. Well, if you just count these 2 scores, divide them by 2, take an average, you have an average sentiment score of 0.75, which is on a scale from -1 to 1, a very positive sentence. Let's take a look at the second sentence then. So this restaurant is mediocre, but it's okay, I guess. Mediocre has a rather negative valence, so -0.1, and okay has a rather neutral or slightly positive valence with a score of 0.1. Again, count them, divide them by 2 to have an average, and you have a score of 0. This is a very neutral sentence, which makes sense if you read it. Then the third sentence, this is a terrible restaurant, the food was awful and the waiter was rude. Again, the computer scans our sentence and matches the words of the sentence with our lexicon, and it detects 3 negative words, terrible, awful, and rude, with a mean average sentiment score of minus 0.6, which is a negative sentence. And this is basically how a lot of sentiment analysis works. It just counts the words, and you have to provide a list of words to the computer to check for with their corresponding label, or in this case, their corresponding score. Another interesting way of using these lexicons is that you can take a dictionary and create another lexicon with it. This sounds kind of strange, but hear me out. So let's take our sentiment analysis lexicon of the previous slide. We could extend this lexicon of positive versus negative words by looking for correlations within the same text unit. This means that the computer will look for the positive and negative words as defined by us humans in the lexicon, and then it will check what kind of words tend to co-occur with said positive and negative words. And it will infer that since these kind of words tend to co-occur with the positive or negative word, that they must have approximately the same kind of valence. Now, this probably still sounds like Chinese, so let's take a look at a specific example. This is a terrible restaurant, the food was awful and the waiter was rude. Now, imagine that we don't have the words awful and rude in our lexicon, but we do have the word terrible as a negative word in our lexicon. Now, the machine can look for patterns in the text and can infer that awful and rude are 2 words that tend to co-occur in the same sentence with the word terrible. Thus, they must have approximately the same, in this case, negative valence. Of course, this is not a perfect method, since that a sentence doesn't contain one emotional valence per se. Let's take the example of a sentence. This is a terrible restaurant, but the waiters were great. In this case, great and terrible have opposite emotional values, but overall, if you feed the algorithm enough text and enough examples, usually it will refer that emotional positive words will tend to co-occur with other emotional positive words and vice versa. This is also an interesting example of how knowledge engineering and machine learning can be combined. So we feed the machine knowledge about our language, namely this is an example of a positive word, this is an example of a negative word, which is typical for knowledge engineering. And the machine learns by itself, by looking at patterns in the text, that there are other positive and negative words. And this pattern seeking and learning from the ground up is typical for machine learning. So this is an interesting combination of the 2 intellectual traditions. Lexicons can also incorporate rules to deal with spelling errors, to create rules for emphasis, negation, shift in tone, punctuation, etc., etc. Let's take an example here. The sentence, "The actor in this movie really sucks, but the movie itself was not bad at all." This is a complicated sentence for several reasons. First of all, there's a shift in tone. So the first part of the sentence is negative, the second part of the sentence is positive. We could incorporate a rule that says that whenever the word but is present in a sentence, that we must put a higher weight on the second part of the sentence. In this case, this means that overall the sentence is rather positive, although it started off pretty negative. You also have one intensifier here. The word really before sucks. Really sucks means that the actor was really bad, so we must put a higher negative emotional weight to these to the word sucks. Above all, the word sucks is also misspelled, so we could feed the algorithm a list of words with their misspellings and how you have to spell them in a correct manner. And you also have negation here. So the movie itself was not bad at all. Bad is a negative word. If we would just count the words as they are, well, we would evaluate the entire sentence as negative. So we could incorporate a rule that says, okay, if not precedes a word with a particular emotional valence, you have to reverse the emotional valence. So not bad is positive, and although bad itself is a negative word. This means that we have to come up with rules ourselves and feed it to the algorithm. So the computer in this sense stays rather naive. And this is typical for knowledge engineering, that humans have to come up with all kinds of rules to feed a computer how it should interpret and understand language. These are some well-known dictionaries, the LIWC and the General Inquirer. You can click on the links and have a look at all the different word categories that they have. So, for example, the General Inquirer has a relatively specific sentiment analysis categories. So they have words that express hope, anger, sadness, fear, etc., etc. And we can basically count the words in our text and put a certain score based on those counts. Now let's look how this actually works in reality. How do we use lexicons, and how do we go from a raw piece of text to a piece of text that can be analyzed by a computer? So this is what the basic process looks like. We start with raw text, and at the end of the process we have a bag of words model which can be analyzed by a computer. Let's take a look at each of these steps. So the first thing that you want to do is you want to tokenize your raw text. Let's take a look at an example here. So you have the sentence, I'm learning about sentiment analysis and I never had so much fun in my entire life. If you load this sentence into, let's say, Python or R or any other environment, these are just a bunch of characters. It doesn't have any meaning because a sentence doesn't have any structure. So the first thing that you want to do is put some structure to that sentence. And how you do that is you divide a sentence into their smallest symbolic units. And in our language anyway, the smallest unit that carries meaning are words. So tokenization splits the raw text in meaningful units, and those are words. And this is what I've done exactly here. So I've fed the sentence to a parser in Python. A parser splits up the sentence or splits up a text and assigns some meaning to it. And the first thing that it does is it extracts the words out of a sentence. And you can see that it did a pretty good job. The basic rule, of course, is that a space means there is a new word, but it's also smart enough to split the I and the M, although there's no space between them. The next thing that you want to do is do part of speech tagging. Now, a part of speech is a category of words with similar grammatical properties. Think about the categories nouns, verbs, adverbs, adjectives, you get the idea. And we want to assign to each word in our sentence the appropriate word category. And this is what my parser exactly did. So it identified the word I as a PRP, which stands for pronoun. M is a verb, learning is a verb. Sentiment and analysis are both nouns indicated by double N's. And the word and is a conjunction indicated by double C's. Now, why is this important? Well, there are a couple of reasons. The first reason is that different parts of speech might have different meaning, and this is relevant for our further analysis. There's a good example here in Dutch with the word ongelooflijk. Ongelooflijk can both be a positive word or a negative or a neutral word. So, in the example sentence, het concert was ongelooflijk goed, the word ongelooflijk is an adverb. And it indicates clearly a positive sentiment, a positive emotion. But ongelooflijk can also be an adjective. For example, in a sentence, dit is echt ongelooflijk. Which can indicate, well, anything. It can be positive, it can be negative, and it can be neutral. A second reason why you want to do part of speech tagging is that you only want to extract or analyze a certain category of words. Let's imagine that you have a sentiment lexicon, but it only contains adverbs or adjectives. Well, if that's the case, it's useless to keep the other word categories in your text data. You can just do without them. Especially when you analyze, let's say, 1 million documents, well, it can be computational difficult to keep all the words in your bag of words model. And you only want to keep the word category that is actually included in your lexicon and is relevant to your analysis. A third reason is because assigning a word category is the first step to understand a sentence. And it's therefore also used to assign chunks to words in a sentence. A chunk is basically a series of words that within or even within a sentence have some symbolic unity. For example, you can see it in the third column here, in the chunk column with the hats. You can see that so much fun is one chunk and my entire life is also a chunk. So they're basically a series of words that belong together, that without their unity, they don't have that much meaning. And this is called dependency parsing. The next thing that you want to do is selecting relevant features. Now, what is that and why is that important? First of all, natural language contains a lot of noise. What do I mean by noise? Well, a lot of our utterances or the text that we produce contain words that are very important to assign the appropriate meaning to that text, but the words that we use are so common and so often used that they're not predictive for any particular natural language utterance. And those words we call stop words. We want to remove those stop words so that the algorithm can focus on the important words in our text. Here is again our example sentence. So I'm learning about sentiment analysis and I never had so much fun in my entire life. Although all those words are very important to assign a correct meaning to that sentence, the words I am, about, in my entire, and the word and I never had, etc. are so common that we can just delete them because they're not predictive for any particular utterance as such. I have some other examples here of subwords, so like words as them, who, those, all pronouns, the verb to be, is, this, themselves, herself, hers, we, etc. Those are all words very important to assign appropriate meaning, but they're irrelevant for predicting a particular type of text, and so we delete them. The next thing you want to do is stemming or lemmatization. Now, why is it important? It is important because natural language contains a lot of inflected word forms, such as conjugated verbs. Let's take the example of a couple of sentences. I am fighting, he fights, I will fight you. All those three sentences basically refer to the same kind of action, namely, someone is fighting. And we want to make these sentences more uniform so that the computer knows that we're talking about the same type of action. And this is exactly what stemming or lemmatization does. It brings these inflected forms back to their root or lemma. And there are two ways you can do this. Lemmatization is a smart way of doing this. It uses extensive dictionaries to bring words back to what they call their lemma. In other words, it uses knowledge as engineered by humans that we feed to the algorithm about the inflected verb and word forms. Here are a couple of examples. So, he bought several cars is an entirely different sentence than he's buying a car right now. Still, both sentences basically refer to the same type of action. Someone is buying a car. So we want to uniform these sentences. And this is what we get after lemmatization. So he bought several cars becomes he buys several car. Bought, we bring it back to the infinitive form, buy, and cars, the plural form, becomes back singular, car. He's buying a car right now then becomes he buy a car right now. So you can see that after lemmatization, these two sentences look more alike. Stemming is basically the dumb cousin of lemmatization, and it uses straightforward rules to bring words back to their root. A rule for example, could be whenever you have a word and the last letter is an S, if you do away with the S at the end, you have the singular form. So, for example, with stemming, boy and boys both could become boy, right? So this is a very straightforward rule. But they produce some odd results from time to time, and they're often only used when dictionaries are not available in a particular software package. For example, in Dutch, we still have to do some stemming in some software packages. But you could create some odd results. For example, the words spoor and the plural form sporen can be stemmed to spor, which is kind of strange. Now let's take our example sentence from earlier about sentiment analysis, and let's look at their lemma. So you can see that I am becomes IB, and I am learning becomes IB learn. You see? Yeah, the algorithm does a pretty good job here. And finally, you want to construct a bag-of-words model. Now, what is a bag-of-words model? It basically means that you convert your textual data to a format which is suitable for analysis for a computer. In reality, this comes down to collecting all the words in your database of texts and convert it to a data frame where each word is one variable. Each text unit can score 0 for not present and 1 for present in the text unit on each of these variables. So let's take a look at our first sentence. Our first sentence is, "This is terrible." And it scores 1 on the variable this, be terrible. You can see I already did some lemmatization here. So the is has become be. And I also indicated the columns this and be in red. Why is that? Well, because these are typical stop words, and so in reality, these words would be already deleted from my textual data. Let's look at the second sentence then. It scores 1 on the column and this word this, be, restaurant, and great. You could construct a sentence from these 4 words, like this restaurant is great. This is probably the sentence we're talking about here. You can see in this bag-of-words model that the position doesn't matter. It only indicates whether a certain word is present in the text or not. That's about it. It doesn't care about the order of the words, which is a hefty limitation of the model. And it's a simple model because of this reason. We are ignoring grammar, sentence boundaries, paragraphs, and other contextual info. But there's also a positive side to a bag-of-words model, obviously. It's simple and it's therefore also useful. We can simply count the words by treating them as variables. So, in this case, we can see that the second sentence has a 1 on the variable great. So, this is a positive sentence, right? You can simply count the words just like if you have done a survey, you can check the scores on different questions. You can here check the scores on different words. Although lexicons are prevalent and even necessary for NLP applications, they are usually not enough for a computer to reach a true understanding of human language. Now, why is that? This has everything to do with the aforementioned distinction between knowledge and learning. So, on the one hand, we can't go without these lexicons. We need to feed a computer a structure of our language, so that it knows, for example, that I am is an inflected form of to be. This refers back to the importance of knowledge engineering. In other words, we humans use our understanding of language to instruct an algorithm very explicitly how it has to deal with textual data so that it understands language. But I'm afraid that's not enough. We already saw when it came to sentiment analysis that we have to incorporate some rules to make more valid estimates. We saw some rules, for example, to take into account the shift in tone within a sentence or negation, but these are some very straightforward examples. If you want to make sure that an algorithm actually understands and estimates the meaning of our natural language use accurately, we probably need a billion and a billion more rules. And this is simply impossible. And this is why machine learning is important as well, so that the machine learns from examples. Let's take an example here. So what about sentiment analysis? Can we define some clear-cut rules to detect sarcasm? For example, if I read the sentence, "That was a great movie, lol not," it's pretty clear that this first part of the sentence was meant to be sarcastic. But can you define a very clear-cut rule that we can feed to an algorithm to detect sarcasm? Not really. That's going to be very difficult. Let's go back to the labeling exercises we talked about earlier. For example, the research that tried to categorize news articles as being dramatized or not. Now, what does it mean that a certain piece of text is dramatized? Are we looking for a specific set of words? If so, what are the words then? And what about even more complex constructs, such as a toxic tweet or a toxic message on Facebook or whatever? What does it mean that a certain utterance is toxic? Again, do you have like a list of words we need to check? No, that's very difficult to pinpoint, because in everyday reality, we use concepts in our language that don't have very clear-cut definitions. We use them with much confidence and we're pretty sure that we have an understanding of what they actually mean, but it's very difficult to formulate a rule and to feed it to an algorithm to detect a certain construct or property in a text. And this is again why machine learning is very important. So let's talk about machine learning. When we talk about machine learning, we don't refer to the knowledge part anymore of NLP, but obviously the learning part. Machine learning is all about learning from data and from examples and patterns present in data. Professor Frederik de Grove will give a lecture specifically on machine learning, so I advise you to watch this lecture as well. I will give you just a basic understanding of machine learning when it is applied to NLP. So, when we talk about machine learning, it's really important to make a distinction between supervised and unsupervised learning. To understand this distinction, it's important to look at some example data. So here I have 5 different sentences, and I labeled these sentences as being toxic. You can replace the word toxic with rude, versus non-toxic or not rude. So the first sentence is obviously rather toxic. "Just piss off, you prick." Okay, pretty rude. Then we have 2 non-toxic sentences. "Well, I respectfully disagree, sir." And "Okay, point taken, haha." Then we have another toxic sentence. "You miserable prick." And finally, a non-toxic sentence. "Haha, touché, dear sir." Now, imagine that we want to build an algorithm that understands toxicity in language, and that thus can label a specific text, such as a tweet or a longer text, as being toxic or not. If we went with a lexicon or dictionary approach, it means that we need to define beforehand a list of words that are toxic versus non-toxic, and that we feed with thanks to our human knowledge of our language to the algorithm. But this is not how machine learning works. Machine learning works by learning from example and from patterns present in the data. But supervised and unsupervised learning do it in a completely different manner. So, supervised learning learns from example. In other words, it will look at the last column of our data set here, the class, and it will look for words that are predictive for a certain label. And it could infer, and it will infer, as a matter of fact, that the word prick is very predictive for a piece of text that is toxic. And likewise, it will also predict that the words sir and haha only occur when a text is non-toxic. So these words or these features or these tokens, whatever you want to call it, are very predictive for the class non-toxic. And it will just learn from these examples. This means that the modeler needs to interpret the input of the model. It needs to train the model using training data, using examples. Because supervised learning only learns from these examples, it looks for relations between the words that occur or a combination of words that occur in a text and a certain class. This means that the cost of human labor when you want to build such a model is in the beginning stage. It's when you want to generate a lot of training data, you have to do the manual work and you have to infer the class of particular text as being toxic versus non-toxic. And the machine will then by itself learn what is predictive for such a class. Unsupervised learning, on the other hand, learns from the inherent patterns present in the data. So it will completely ignore our last column here. As a matter of fact, when you want to build an unsupervised learning model, you don't need the last column. You just need the data, the text data, and the model will look for patterns that are present in these pieces of text. For example, it will learn that piss off tends to co-occur with the word prick, and prick also tends to co-occur with the words miserable, and some other words probably. So forming a cluster of words. Cluster analysis is a typical example of unsupervised machine learning. This means that the modeler needs to interpret the output of the model, which is different from supervised learning, where we need to interpret the input of the model. So the real work when it comes to unsupervised machine learning for the modeler is at the end of the analysis. So the model can point out that there are different clusters of words that tend to co-occur, but what these clusters actually mean and what kind of label does you have to assign to these clusters, well, that's a mystery for the algorithm. That's something that the human needs to define. Within academic settings, and especially within the communication sciences, NLP is usually applied within a supervised learning environment. This means that we, humans, we do the work beforehand. We label some texts and we give this example set to the algorithm. And then the algorithm will construct a model that predicts the label or the value of a text variable based on the example data. So you do not provide a list of features or words nor a set of linguistic rules to the model like we did with our sentiment analyzer earlier. You just provide it with a set of labeled examples. And the model learns by itself which features, thus words or combination of features, are predictive for a specific label or value. So to sum up, you construct a predictive model based on what we call training data or scene data. These are the labeled examples we provide to the model. And if the model can successfully predict the labels of these texts, well, we can use this model to predict new unseen data. So for example, if we can successfully classify a text as being toxic or not toxic with our toxic classifier based on the example data seen earlier, well, we can just feed the algorithm a billion or an unlimited amount of other texts, and it will predict or estimate with a certain accuracy and precision whether a certain text is toxic or not. This means that supervised learning is really interesting for measuring theoretically relevant constructs. News frames is a good example here. So some researchers already tried to infer news frames using unsupervised learning methods. This means that they just looked for certain patterns in the textual data, and in the end they come up with several clusters of words or combination of words or chunks in sentences or whatever that tend to occur with one another in a singular text. And the assumption here is that a single cluster of words that tend to co-occur with one another refers to a kind of news frame. Now, from a theoretical point of view, this is pretty fishy, because it's not because certain words co-occur with one another that this co-occurrence is theoretically relevant. This is totally different from supervised learning. In supervised learning, you know what you're looking for. So you already have your theoretical relevant distinctions or map or whatever framework in your head, and you label the data based on your knowledge, and the machine algorithm will try to predict the relevant labels that you already decided that you wanted to label. So this is why supervised learning is especially valuable within a research context. Also important to keep in mind is that this model is not only just predicting what kind of words are predictive for a certain label or text like we did in the previous slide, but the model also learns very complex linguistic interactions. And most of these interactions, we, the humans, let's say, are unaware of. We are unaware of what makes or how we could predict a certain text of being sarcastic or not, for example. But if we feed the machine algorithm enough examples of sarcastic texts, then maybe it could come up with a very complicated algorithm that uses multiple features, multiple words, or even order of words that would hint at the presence of sarcasm or not. So this is why the supervised learning goes way beyond, for example, the rule-based lexicons. It's not about just simply including some words that are predictive, but also very complex linguistic interactions, combinations of words, order of words, etc., etc. Now, how does it actually work? We start with a set of example labeled data. Imagine that we want to predict whether a text is positive or negative in tone, which is a typical application of sentiment analysis. We could, for example, gather 10,000 movie reviews which are positive and label them as such. And we could also gather 10,000 negative movie reviews and label them as negative. And these 20,000 movie reviews will be or will constitute our example data. And then we just do the usual pre-processing steps such as tokenization, lemmatization that we discussed earlier. Then we split our example data in a training set and a test set. A training set is the set of data that we will use to actually train our model on. So most of the data will come in our training set. Let's say 80%. The remaining 20% will constitute our test set. So first we will do something with the training set. We will pick an algorithmic model. This can be a very simple model such as the naive Bayes classifier, which we will discuss in the next couple of slides, or it can be a rather complex model such as support vector machines or even neural networks. Then the model will find patterns, and these patterns can be very complex and contain very complex interactions between words, features, and the order of words that are predictive for a certain outcome, in this case whether a text is positive or negative. This is where the actual learning takes place. Then, when we have constructed the model, we will try to apply the model to the test set. Now, it's very important to remind yourself that the test set is labeled data, so we know for every movie review in our case, in the test set, whether it's a positive or a negative movie review. But the model wasn't trained on this test set. It has never seen these examples. So the question here is that now that the model has found some predictive patterns, can it successfully predict the labels of the test set? Yes or no? If not, it will adjust itself to be maximally predictive until we have reached a satisfactory precision and accuracy. And if we have done that, if the model can predict or label our movie reviews as positive versus negative with enough precision, well, we can just use this predictive model to predict labels and values of previously unseen data. And we could just without even knowing whether a text is positive or negative, or a movie review is positive or negative, we could use it to predict this text property. Again, see the article on Ufora, What Can Journalism Studies Learn from Supervised Machine Learning? In this article, we explain this flow in somewhat more detail. Now that you have a basic understanding of the steps you need to undertake to construct a machine learning model in NLP, we will look at the most straightforward example, the naive Bayes classifier. The naive Bayes classifier is the most bare-bones example you can have of machine learning in natural language processing, and it's used in a lot of other domains as well. Because of its simplicity, it's also a very popular model. And notwithstanding the fact that the model makes some very strong assumptions that are almost never met, it still performs relatively well in a lot of contexts. Now, let's take a look at the name of the model first. So, naive Bayes classifier. Why do we call it a Bayes classifier? Well, we call it that because it's a probabilistic classifier. This means that this model will estimate a probability that a certain outcome occurs. So, for example, when it comes to textual data, it will calculate the probability that a certain text is positive versus negative. If the probability of being positive is higher than the probability of being negative, the classifier will label and thus classify the text as positive. It's also a naive classifier. Why? Well, because it assumes complete independence between features. In other words, it assumes that the occurrence of one word in a piece of text is completely independent of the probability that another word occurs. And this is, no pun intended, a very naive assumption. Let's take an example. So, if you have a sentence that contains the word soccer or stadium or football, well, the probability that in that same sentence the word goal occurs is way higher than if it's a sentence containing the words, let's say, basketball, right? So the probability of words occurring in a piece of text is not independent of one another. Words tend to co-occur with other similar words. Still, despite the fact that this assumption is almost never met, the classifier, naive Bayes classifier, does a pretty good job generally. So let's try to build a naive Bayes classifier based on some very simple example data and try to classify emails as spam versus not spam. And we will do that using Bayes rule. Now, Bayes rule basically aims to estimate a conditional probability. Conditional probability means that it wants to estimate a probability given some condition. And in this case, the condition is the occurrence of certain words. So, given that, let's say, I have an email with in the title, you have won the lottery. Well, given that these words occur in a title, what is the probability that this email is spam? And this is what we want to know, right? Because we want to classify emails as spam or not. If the probability is higher than 50%, we will classify it as spam, and otherwise we will classify it as not spam. And this is thus the great unknown. It's what we want to estimate. Now, what is so great about Bayes rule is that you only need to calculate the reverse conditional probability and the general probability to estimate this first conditional probability here. So we need to estimate the probability that certain words occur given a specific text category. Well, we can do that, right? We can provide our model with training data and give it 10,000 emails that are clearly spam and 10,000 emails that we have labeled as not spam. And then we can look at what is the chance that a certain word occurs, certain words occur in a text given that it is spam versus not spam, right? We can do that. And we multiply that with just the probability that an email is spam in general and we divide it with the general probability of the words co-occurring in one email. And if we do that, then we have an estimation of what the probability is that our email is spam given the words in the email. Great. So this is probably still a little bit too abstract. Let's go to a specific example. So we have 4 email subject lines here. I already lemmatized the tokens, I removed the stop words, and the model only uses words because I also included the sender of the email, which is typically a variable that a true naive Bayes classifier for spam email will incorporate in the model. But just for simplicity's sake, we will just focus on the words in the subject line here. So you have a first email sent to you by an unknown address, and it contains the words, "You have won the lottery." Okay, we label it as clearly spam. Then you have an email of your mom that reads, "I bought some lottery tickets." Okay, great, mom. This is not spam. Then you have an email forwarded by your uncle. Oh, great. Here we go again. So the subject line is, "You won't believe this lottery." It's again one of those chain emails that your uncle has sent to you. It's clearly spam. We don't want that in our inbox. Then an email of your girlfriend. It says, "Did you win the lottery?" No, I'm sorry, I didn't win the lottery, but it's not spam. And then a drunk friend of yours has sent you an email in a subject line, "Have you seen my keys?" He has lost his keys when obviously he was drunk at your home. Also not spam. Now, can we use this data to estimate the probability that some new email that will arrive in our inbox is spam or not? Well, yes, we can. So we start off with calculating the probability that the separate words occur. We will just take the first example here from the unknown address, right? So the probability that the word win and lottery occurs. So win only occurs two out of 25 times, which comes down to a proportion of 0.08. Okay, so the probability that the word win occurs in an email subject is about 8%. Then the probability that the word lottery occurs is 16%. All emails except the one of your drunk friend contains the word lottery. So that's 4 out of the 25 words. Okay, 16%. Then we will calculate the probability that an email is spam or not. Well, 2 out of 5 emails are spam, that's about 40%. And then we will calculate the conditional probability. So given that an email is spam, what is the probability that the word win occurs? Well, it's about 1 out of 10 words. Yes, okay. So that's 0.1 or 10%. And what is the probability that a word is lottery given that the class is spam? Well, in both emails that are spam, we have the word lottery. So 2 out of 20 words. So that's 0.2 or 20%. Okay. Now, just using this information, we can calculate the probability that a certain email is spam given these 2 words in your subject line. So this is basically filling in the formula of the previous slide, right? So you fill in the conditional probabilities, you multiply it with the 40% with the probability that an email is spam or not, and you divide it with the general probability that a certain word occurs in an email subject line. And if you do that, well, and if you do the calculations, you can do them by yourselves, the probability of being spam is 62.5%. 100%. Of course, it's based on a very, very simple model. But based on this simple model of only 5 examples, we would classify this email as spam or similar if you would receive a similar email with the words win and lottery in them, and for the rest stop words, we will classify it as being spam. So this is how a naive Bayes classifier works. So what I want you to understand is simply the basic idea, or grasp the basic idea, that the naive Bayes classifier looks at the probability that a certain word occurs, right, given a certain class, and that it estimates from that what the probability is that a certain text belongs to a certain class. And that's about it, right? So don't worry about the specific formula. You don't have to know that. Now, if you want to do a more elaborate exercise, there's a great book by a man named Foreman, I guess it was Furman, called Data Smart. And he builds a naive Bayes classifier completely in Excel. It's a pretty interesting exercise, and it's also very well written, so I can only recommend actually this book in its entirety. Although this was a very simple and basic example of machine learning, and that real machine learning applications are way more complex, I hope that it makes clear the logic behind it all, in the sense that the algorithm here learns to classify emails based on patterns that are present in the labeled data. So it knows what to look for, because we provided with an example set of emails that we already labeled as being spam or not spam. But the question is, what is predictive, or what kind of features are predictive of these categories? And the patterns it's looking for are extremely simplistic, so it's just the occurrence of words. And moreover, it assumes independence of these probabilities. So it assumes that a probability that win occurs is totally independent of the probability that lottery occurs, which is obviously not the case. But still, it learns from examples without relying on knowledge engineered by humans, which was the case when we talked about the lexicon approach. So instead of feeding the algorithm the idea that that words such as to win and lottery are indicative of spam emails, we just provide it with examples, and it comes up with the predictive features all by itself without any human intervention. However, a naive Bayes classifier doesn't care about context. It's just a simple bag of words model. Remember the bag of words model that we already discussed, so it doesn't care about the order of the words. But it's a fast and simple algorithm that performs surprisingly well as long as you feed it a lot of data. So we only based our example here on 5 emails. Well, just try, let's say, 10,000 emails, and let's then see what the algorithm is capable of. Now let's take a look at some of the more complex methods of machine learning. I will only talk about these more complex models in a very superficial manner. So don't worry, you don't have to remember or learn what these separate algorithms do. As a matter of fact, I won't even discuss them separately. Instead, I will just drop them here basically, and I will go more in depth on their general nature and purpose. So, very popular are the support vector machines, the decision trees and random forests, and of course the neural networks, which is based on the way our brain learns and works. All of these methods are called black box methods or models. Why is that? Well, it's because the algorithm learns a lot of complex interactions from the data, but it's very hard to decipher what the actual decision process within the model looks like. it's pretty clear what the input of each model is. In our case, when it comes to textual data, we can feed it, for example, 10,000 emails, which we have classified as either spam or not spam. And we feed it to an algorithm, and it will learn some complex interactions between words, order of words, etc., to predict whether an email is spam or not. The output of the model is also pretty clear. The output of a machine learning model is a prediction or an estimation, in this case, whether an email is spam or not. And we can even check whether these predictions are worth anything by putting the model loose on our test set of labeled data and check whether the estimations of our newly trained model corresponds with the labels we gave on these emails. But what is a little bit more difficult to decipher is what happens in the middle. So the input is clear, text, the output is clear, prediction, but how the model reaches this prediction is pretty unclear. And this is what they call, metaphorically, the black box. Now, this is precisely because in these machine learning models, different features, words, order of words, can interact with one another in a very complex manner to predict the outcome. And in this sense, because they're more accurate and they can incorporate more complex interactions, there is an inherent trade-off between how accurate a model is and the interpretability of a model. So let's compare our naive Bayes classifier. Our naive Bayes classifier is pretty straightforward, and it's also very transparent. We could ask the model for each word in our labeled training data, what is the probability that an email is spam, for example, given that the word, let's say, surprise, is in the subject line. And the model can just give us an output between 0 and 100%. Now it can do that because the model is very simple. It also has a very naive assumption that a probability that surprise occurs in a certain email is completely independent of the probability that any other word occurs, which is yet again a naive assumption, which is often not true. These more complex models, such as the support vector machines, can incorporate very much more complex interactions. And these interactions can be so complex that they don't even make any sense to us humans. It's just the machine looking for the most optimal way of learning and to come up with rules by itself. It's a very, very basic understanding of our language to predict a certain outcome. And that's about it. It doesn't have to make sense to us humans as well. And often it doesn't make sense. So when we look at, for example, the more complex methods like the text generator demo I've showed you in the beginning of the lecture, the demo has been fed 8 million web pages, and based on the very complex interactions of words in sentences, in paragraphs, in text, etc., of these 8 million web pages, it estimates the next word in a sentence given a prompt. Remember? Well, it's completely impossible for us humans to have some understanding of how this model works. It's just based on a lot of data, and how it reaches the decision to display a next word given the previous words in a text is completely unclear to us. Of course, there are methods to make, for example, neural networks or certainly decision trees and etc. more transparent, and you can do that, but in some essential sense, these more complex machine learning methods remain a black box by definition. Now, remember that near the beginning of the lecture, I told you that today we still need knowledge engineering in NLP. We still need to feed the algorithm a basic understanding of how our language works. For example, we need to feed it the idea that there are verbs, there are inflected forms of these verbs, like to be and I am, etc. Nowadays, there are some new innovations that even try to automate this knowledge engineering part of NLP. And they're pretty interesting to look at. I will only describe them in a rather superficial manner, and you only have to know the basic idea behind them. So these techniques are called word-to-vec techniques, which is a set of techniques which relatively recently invented around 2013. And what these techniques try to do is they automatically build relationships of similarity and dissimilarity between words. And by doing that, they also try to automatically, in an implicit manner, attain some understanding of language as well. It does that first by trying to estimate the next word in a sentence, or trying to estimate the context, the word surrounding a word. Okay, this is way too complex, so let's unpack that. So let's say we want to know the distance between the word king and all other possible words. So if we have king in a sentence, we will try to predict the next word after king. If we remove the stop words, of course, and all the other irrelevant tokens. Or we will try to predict what in any way is surrounding the word king. It is pretty likely that if we're talking about a king, that somewhere in the neighborhood of mentioning the king, we also mention the queen. If we talk about anyone else, it will be the queen, right? And we can calculate a distance measure between these two words, between the words king and queen. And they will be pretty similar and so have a short distance. Okay, now let's take a second example. Let's take the word boys. And we'll try to estimate what kind of words will appear next or around boys, or the word boys. Well, it's pretty likely that somewhere in the neighborhood of mentioning boys, if we mention someone else, it's maybe or probably girls, or that's more than likely. Okay, we can also calculate a distance measure between these two words, boys and girls. Also pretty similar. Now, this is where the interesting part comes in. So not only will words that tend to have a similar meaning cluster together, but we can also compare the distances between word pairs. In this sense that the distance, the similarity or dissimilarity distance between king and queen will be the same or almost the same as the distance between the words boys and girls. And in this sense, implicitly, our model has learned the meaning of the word king and queen. Namely, it has learned that king is to queen as boys are to girls. And it's very implicitly, it has learned that a king is a boy or a man, and a queen is a girl or a woman. Now, it's not exactly like that, but this is the basic idea here, that you calculate distances between words based on their occurrence or the likelihood that they occur around another word, and that you can compare these distances to learn about language. Okay, let's take another step back. So, because of these distance measures, words with a similar meaning will cluster together, right? So king will cluster with queen, and boys will cluster with girls. Okay. Here's another example. So we have three example sentences here, and they all talk about animals. So example 1, my Uncle Jimmy was a farmer and had 2 horses and a pig. Example 2, back in the day I had a pig and a dog as pets. And example 3, cats and dogs usually don't get along. So Word-to-vec techniques will pick up that all these sentences are basically about the same subject, about animals. And the words pig, dog, horses, cat and dog, etc., they will cluster together with relatively small distances between those words. Okay. Now, again, the really interesting thing here is that words with a similar distance have similar relations, right? So this is step 2. Let's take an example here. The distance between Donald Trump and the word Republican will be the same as Barack Obama and Democrat. So the model has learned something. It has learned that Donald Trump is to Republican as Barack Obama is to Democrat. Similarly, it will learn, for example, that China is to Taiwan, which are two very estranged, conflicted neighbors, let's say, in the world. So China is to Taiwan as Russia is to Ukraine or Russia is to Armenia. Similarly, it can also infer implicitly the inflected verb forms of several verbs, in a sense that if you look at the image on the slide, drinking is to drank. In other words, the distance between drinking and drank is the same as the distance between swimming and swam. So, without instructing the machine learning algorithm anything, it has learned relationships and similar meanings. Let's take another example here. So I've plotted here the distances between different countries and their capital. Now, imagine that you have no idea that, let's say, the capital of France is Paris, right? That you're completely oblivious to that fact. But you do know that the capital of China is Beijing. Well, purely by knowing that the capital of China is Beijing, you can also infer what the capital of France is. So China is to Beijing as France is to Paris. All right, so in this way, the model actually learns the relationships between countries and their capitals, and you haven't even instructed it to do so. It's just because all these capitals tend to co-occur in the same neighborhood as their countries, such as Italy, Greece, Spain, Portugal, etc. Now, if this is still somewhat a mystery to you, don't worry about it. Just have a basic idea of why this is possibly replacing partially the knowledge engineering part of NLP. We will end the lecture with some current issues in natural language processing. One of the main issues in NLP in general is that we need a lot of data to feed our models, to feed the computer so it has a very basic understanding of how our language works. And this is because, as I've mentioned earlier, there's a lot of noise in language as generated by humans that prevents us from detecting the signal. So we have the signal, which are the very predictive words or combination of words or order of words. But this is getting overridden by a lot of stop words that we use, words that are not predictive at all for any specific utterance. The problem is that although we need a lot of data to train our models, there are only a few high-resource languages in the world. With a high-resource language, I mean a language that has a lot of digital data available, and preferably labeled data. And this is why all the fun and all the exciting stuff is happening in the English language in the field. A good example of this is trying to do NLP in Dutch. if you follow the sentiment analysis workshop, it will be clear that we will encounter some limitations on that in that regard. Second problem is a strong specificity in domain, context, and time. So even if we have a lot of data, if we train a model on a large set of example data, labeled data, then still this model has only a limited applicability. Let's take an example of context applicability. Imagine that you train a news classifier to classify a certain news article as being dramatized or not dramatized. If you train the classifier based on news articles from The Guardian or the New York Times, this model will have some trouble predicting whether a news article is dramatized if it sees an article from The Sun. Why? Well, because The Sun is a tabloid paper, and a tabloid paper uses totally different language than The Guardian or the New York Times. Domain specificity is similar to that. So imagine that we train a classifier whether a text is positive or negative based on data from politicians. Well, it will be difficult to detect positive versus negative emotions in, let's say, movie reviews or reviews of customers on Amazon, because it's trained on data as used by politicians, and they also use different kind of speech and words. When we talk about specificity in time then, it's very clear that even if our model is perfectly able to predict or even generate text or textual properties, this predictive quality will diminish over time. This is simply because language changes. The way we speak today is different than the way they spoke 100 years ago. So even if we have a perfect model today, it will be practically useless in, let's say, 100 years, and especially a couple of 100 years. This is also something that we talk about in our article that is on Euphora. Issue number 3, classifiers work well for relatively straightforward and common concepts. And this is something that you see in the academic literature as well. So it is also an explanation of why we see so much examples of sentiment analysis. Because sentiment, although emotion is a very complex concept, if you translate it or reduce it to polarity, negative -1 versus positive 1, remember, then it's a very straightforward concept, and you can build a classifier on that pretty easily. The problem occurs that some other concepts are too complex, or especially if concepts are not as prevalent, so you don't have a lot of data to measure the concepts, then it's a whole lot more difficult. A good example is, again, news frames. So you have some generic news frames as formulated by Valkenburg and colleagues, but you also have issue-specific news frames. For example, around the coronavirus, well, there are probably some news frames that are issue-specific, right? Maybe you can have let's say, an apocalyptic news frame about the coronavirus, which states that it's the end of the world, and this is how it's framed by the media. But because you don't have that much data or news articles about the coronavirus, it's not easy to predict this issue-specific news frame. And what we get then, where we arrive at, is an issue of what we call algorithmic determinism. Algorithmic determinism is basically the idea that because the algorithm is only capable of measuring very straightforward, simple, common concepts, that we will just only study straightforward, simple concepts. And that thus the limitations of our algorithms will steer the research we do and will steer theory in the end in the social sciences. This is also something that we talk about again in the article on Euphora, so I recommend it that you check that one out. 4. Humans are not robots. Context remains an issue. Even with all the fancy machine learning algorithms of today, it's still very difficult, for example, to detect sarcasm. And this is because whenever someone speaks to us, we don't only take into consideration the speech as such. We also take into consideration the context and the person who's speaking to us. Let's take a very sarcastic friend. He or she has a very specific personality, intentions, communication style, emotions, and other characteristics, such, for example, he or she has very dark black humor. Because of all these characteristics of this specific person, it's very easy for you to A, estimate that this person tends to be sarcastic, and B, to know when this person is sarcastic and when he or she is serious. But this is completely impossible to infer by a computer. Even if it has a lot of text data of this specific sarcastic friend, it only has the speech. It doesn't have the other characteristics. For example, the fact that he or she tends to have dark humor and that characteristic tends to be predictive for being sarcastic. And all other nonverbal cues as well. So this is still an issue within NLP nowadays. Context. 5, and finally, implicit biases. This is a typical problem for machine learning algorithms in general. You probably heard some example in the news about how machine learning algorithms reproduce inequality. So let's say that you have an engineering firm and that you want to automate the hiring process, and you want to construct a predictive model to estimate whether a certain candidate should be hired or not. And you feed it the historic data of your HR department. So you feed it all the CVs you've ever gotten, and you also feed it, of course, since it's supervised learning, the label hired in the end or not hired in the end. And based on these labels and whatever is predictive in a CV of belonging to the label hired or not hired, the model will produce a certain prediction. Now, if you were somewhat sexist in your hiring process before implementing the machine learning algorithm, the machine learning algorithm will just replicate this bias and will tend to hire more males. For example, it will find out automatically and implicitly that names such as David and Bart are much more likely to be hired than names such as Karen or Laura. So it's not that the machine learning algorithm is somewhat sexist, it doesn't have intentions, it just replicates reality by looking for correlations or underlying correlations that are indicative of your sexism. And this goes for every classifier as well, also within NLP fields. So if reality is biased, your model is biased. And I have a good example of this. So I came across this on Twitter a couple of days ago. What you see here in the right corner is the output of the Perspective API. And this API has the goal to classify certain texts as being toxic, so in other words, rude and offensive, versus not toxic. And someone pointed out that there is a racial and gender bias going on in this classifier. Let's take the first sentence as an example. So, your criminal justice system in the USA is extremely racist. If you feed that to the algorithm, it will tell you, based on its predictions, that it's 71% likely to be toxic. However, if you feed it basically the same sentence, but you just deny it that the USA is racist, so you say your criminal justice system in the USA is not extremely racist, then it will give you a very low probability that the text in question is toxic. Which is weird because it's basically the same sentence, but it's just with a negation. And this is yet another example of how machine learning algorithms, if your training data, if your labeled data is biased as a racial bias, it will just reproduce said racial bias. Okay, that's about it for today. I hope you enjoyed the lecture and that you now have a basic understanding of some of the concepts of NLP and what the field is all about. If you are interested in artificial intelligence or machine learning, I can recommend you to books for further reading. You have The Master Algorithm by Pedro Domingos, which is a book that starts from scratch. It doesn't assume any knowledge about anything at all. And it's a pretty entertaining book. And I also recommend you to read Super Intelligence by Nick Bostrom, which is a little more of a serious read and also a little bit more abstract, but it's very well written. Okay, that's it. I wish you all a very nice day. Bye.